In this lecture, we will discuss reinforcement learning from the perspective of deep learning. Reinforcement learning is a field which is independent of neural networks in general. In fact, you can have reinforcement learning algorithms that do not use any type of deep learning or traditional machine learning algorithm as we know it. The goal of deep learning, however, is to be able to work with real life settings of reinforcement learning. As we'll see, traditional reinforcement learning is inadequate to handle real life situations with a large level of complexity. This video will focus on traditional reinforcement learning. In fact, it will give some simple algorithms for traditional reinforcement learning and then discuss why deep learning is always needed to be paired with traditional reinforcement learning in order to make them work for real life settings. The goal of artificial intelligence is to simulate the complexity of the behavior of living organisms. When we look at living organisms or when we look at human beings, their behavior might seem very complex. For any given situation, there might be a complex set of behaviors that an organism might perform. However, in reality, behind all this complexity, there is a certain level of simplicity. And this comes from Herbert Simon's ant hypothesis. Herbert Simon stated that when you look at human beings as behaving systems, they're actually quite simple. The only reason why biological organisms seem complex is because they inherit the complexity from their environment. So what is meant by this hypothesis? If you look at human complexity, it is caused by the fact that humans are reward-driven entities. So in fact, human behavior is quite simple. It is always designed to maximize its reward. And all of biological intelligence is owed to this simple fact of earning rewards. Now, this type of intelligence, it has been gained over a long period of time. It has been gained over millions of years of evolution. It's also gained over the lifetime of a single individual. But in all of these cases, the simple goal is always reward driven. And that is what gives humans their complexity. Since the goal of artificial intelligence is to simulate biological intelligence, reinforcement learning attempts to simplify the learning of complex behaviors by using reward-driven trial and error. So, when do we use reinforcement learning? What kinds of settings are most appropriate for reinforcement learning? In general, systems that are simple to judge but hard to specify. So, for example, if you look at a video game, for example, an Atari video game, it's very simple to judge how well a player is doing because the video game, the virtual environment gives you points depending on how well you are doing. But if it's a complex game, it's very hard to program a computer to play that game. Similarly, if you look at board games, for example, chess has a certain level of complexity which again, sometimes it can be a bit difficult to program a computer to play it. Of course, at this point in time, we have computers which play chess, but for certain kinds of games like Go, it's even harder to program computers to play them. Similarly, robot locomotion and physiomotor skills. So typically how well a robot is performing its task, you can give the robot a virtual reward. But again, it's very hard to program the robot how to keep its balance, how to move in every possible situation. And similarly, in self-driving cars, you might have a wide variety of traffic conditions, and it's always very difficult to explicitly program a car to drive accurately and safely, but it's very easy to judge when a car is performing well in terms of its self-driving behavior. So reinforcement learning is also very useful in settings where it's easy to use trial and error to generate data. Now note that it's not in all settings that we can easily generate data using trial and error, but certain types of environments, for example games, it's very easy to use trial and error by playing a computer against itself to generate a very large amount of data. So reinforcement learning can be a gateway to general forms of artificial intelligence, to what the ultimate goal of artificial intelligence, because it tends to simulate most closely what we as living organisms try to do. So then the natural question arises as to why we don't have general forms of artificial intelligence. Why don't we see robots that behave like living beings? There are several reasons for this. One is that reinforcement learning requires huge amounts of data in order to perform the learning. So typically this learning is performed by trial and error, where the system generates the data by trial and then it learns which actions are optimal, which actions earn rewards, and that's how reinforcement learning proceeds. Now, this type of setting, it's possible to generate lots of data in some game-centric settings. So for example, if you look at a setting like chess, it is relatively easy to generate a lot of data by playing a computer against itself. On the other hand, if you're looking at, for example, a setting like a robot, it's not that easy to generate a lot of data. So if you have a physical robot, that robot could break when you're trying to experiment with it using trial and error. Of course, if you had a virtual robot, then it's much easier to experiment with. And that's why, again, if you look at the results we currently have, virtual simulators of robots, we can train them very well, but physical robots, generally, it's much harder to train. So that's one reason, the paucity of data, the difficulty in generating enough data with trial and error. The second challenge is that biological reinforcement learning includes some unsupervised learning. Now, the reason it uses some unsupervised learning, in fact, if you look at a number of synapses in our brain, it's larger than the number of seconds we live. So, if we only performed goal-driven learning in our lives, it would not be sufficient to even fill the number of synapses we have. So, there must be some unsupervised learning going on. What is meant by that? That means that we always look at the environment, not necessarily in a goal-driven way, take in information, and then we somehow know how to use it. That's unsupervised learning. And even though there have been recent advances in unsupervised learning, we haven't quite mastered that art yet. Together with the paucity of data, these are the reasons why reinforcement learning hasn't reached the levels of general forms of artificial intelligence. In fact, even if you look at biological living beings, how they have learned over the years, part of it is through evolution. So we carry on a lot of data from generation to generation, and if you look at all living beings, it's like a massive parallel processing system where all the biological organisms are learning in parallel through trial and error, and they're passing on their knowledge to the next generation. So we are talking about massive amounts of data we have generated over millions of years to learn our complex behaviors, and we have nothing which matches that. But nevertheless, in the few systems where we can generate lots of data, so for example, in some closed-end game playing systems, we have seen some very promising results which tell us something about the promise of this general area for the future. So let's look at the simplest reinforcement learning setting. The simplest reinforcement learning setting is that of multi-armed bandits. Now, this is a very, very simple setting, but it's very important to go through this setting because it gives you the intuition for more complex forms of reinforcement learning. So we start off with multi-armed bandits and then we'll get increasingly more complicated. So what's the multi-armed bandit problem? So imagine you have a gambler in a casino. The gambler has two slot machines in front of him or her. And the gambler suspects that one of these slot machines pays more than the other. So each trial of the slot machine is going to cost the gambler $1. And it will pay $100. So if the trial is successful, it will pay $100 with some unknown low probability. So that probability will typically be lower than 1% because the casino always makes money. So let's assume that the gambler's suspicion that one slot machine is better than the other is correct. So one might be paying with 0.5% probability, another might be paying with 0.4% probability. So there is some small difference. And the question is, what should the optimal strategy be for to play the slot machine, assuming that the gambler's suspicion is correct? So because when the gambler will play the slot machine, he will see which one is giving him more rewards on the average over time. And then he can somehow exploit this. So here we have a stateless model. What do I mean by stateless model? That means that the decision faced by the gambler at each timestamp is the same. Now, traditional reinforcement, conventional reinforcement learning are not stateless models. So for example, if you have a self-driving car, depending on where the car is, what the state of the car is, the action depends on that. Here the optimal action is always the same, which is to play the best slot machine. Of course, since the agent, the gambler, whom we call the agent, doesn't know which slot machine is better, they won't be able to exploit this optimal strategy. But nevertheless, there is no notion of a state, and the state is the same at each time, which is why this setting is so instructive, because it's a stateless setting. So, what should the strategy of the gambler be? Now, the gambler can, for example, play both slot machines alternately, and the gambler can learn their payoff over time. So, by playing the slot machines alternately, the gambler is learning slowly over time which slot machine pays more on the average. But the problem is that this is wasteful exploration, and the gambler wants to exploit the winner as soon as possible. So clearly you can see that there is a trade-off between exploration and exploitation, and this is the hallmark of lot of reinforcement learning settings, where you have this trade-off between exploration and exploitation, where you obviously exploiting as early as possible seems greedy, but often it will result in long-term suboptimal strategies. So let's look at an example of this type of dilemma between exploration and exploitation. So in this case, this is a naive algorithm. In exploration, you play each slot machine for a fixed number of trials. So let's say you decide that for each slot machine, I'm going to play for 100 trials. And then after I play each slot machine for 100 trials each, I'm going to pick the slot machine that wins, that gives me the most payoff, and I'm going to play that forever. That's the gambler strategy. This is a naive strategy. The problem is that there is this trade-off between exploration. So, for example, if the gambler plays too few trials, they might actually play the poorer slot machine forever. So, for example, in this case, because the payoff of the machine is less than 1% probability, and if you pay 100 trials, on the average, only one trial will be a success in the 100 trials. And just by chance, it might happen the poorer slot machine might give you a payoff once, whereas the better slot machine might not give you any payoff. So, what you need is a larger number of trials. So if you use a larger number of trials, again, of course, it's wasteful. You're spending more time in exploration, but it's wasteful. So this trade-off causes a dilemma for you. The other problem with this naive algorithm is that no matter how many number of trials you play up front, there's always a non-zero probability that you will play the loser forever. So we want some kind of strategy which, at least in steady state, over a very long period of time, guarantees you that you will be playing the correct slot machine most of the time. So one such algorithm is called the epsilon greedy strategy. So this strategy probabilistically merges exploration and exploitation. So the idea here is that you play a random machine with probability epsilon, and you play the machine with the highest current payoff with probability 1 minus epsilon. And the main challenge here is in picking the proper value of epsilon, because the larger the value of epsilon you pick, the more you are exploring. So it's the trade-off between exploration and exploitation. And a common strategy is to use annealing. So you start off with large values of epsilon and you reduce it slowly over time. Eventually use some non-zero value of epsilon, some small non-zero value of epsilon forever. And one advantage of this strategy is that you can show that in the long term, typically the winner will be picked. So it's a near optimal strategy, because you're still always wasting a fraction of the trial using exploration, because always a fraction epsilon of the trials will be exploration trials. But nevertheless, it's a near optimal strategy in steady state, unlike the naive algorithm where you could have easily picked the wrong slot machine forever. Then you have the strategy called upper bounding. This is the case of the optimistic gambler. So what the gambler does is that the gambler calculates an upper bound on what he can earn from the slot machine. Now obviously if he hasn't seen a slot machine, then his upper bound will be higher, because he doesn't know much about it. So he what he'll do, he'll look at the average payoff he has received so far, and then he'll add a bonus to it. Now that bonus depends on his uncertainty. The more uncertain the gambler is about that machine, the larger the bonus he's going to add to it. And that bonus is calculated using an upper bound. And so obviously the gambler is being optimistic towards rarely played slot machines. So that gives you the exploration component. So how is the gambler going to do it? So the gambler is going to empirically estimate the mean mu I and the standard deviation sigma I of the payoff of the ith machine using its ni trial. So assume he has played each slot machine so far for ni trial. And he's going to pick the slot machine with the largest value of mean plus confidence interval. So this confidence interval is like the optimism portion. So you can see this confidence is essentially the sample standard deviation. So if he has played a slot machine ni times, the standard deviation of the gambler's estimate will reduce, obviously, because he knows more about that slot machine. So you can show that the sample standard deviation of the mean of the payoff of that machine is sigma I divided by square root of ni. This square root of ni in the denominator is crucial because a slot machine which is played more has less uncertainty because the gambler can reduce its standard deviation, so its upper bounds are lower. So this will tend to favor the slot machine which is played less. It will encourage exploration. So, and the value of k, it decides the trade-off between exploration and exploitation. So the larger the value of k, the more you will explore. Now, all of these three strategies, they serve as basic templates, which are also used in conventional reinforcement learning. So in conventional reinforcement learning, you use some of these strategies as subroutines when your models are not quite as simple as, for example, the multi-armed bandit setting. So let's look at the comparison between multi-armed bandits and classical reinforcement learning. Now, multi-armed bandits is in fact a special case of reinforcement learning. It is the simplest form of reinforcement learning because the optimal decision for the gambler is the same at each step. It's only because the gambler has imperfect knowledge that they cannot make the same decision at each step. That's why the optimal strategy is not always to play them. But the state of the system, the way the environment poses the problem to the gambler is identical at each step. The slot machine is always the same. Both slot machines are always the same. They always give the same payoff. So the environment that the gambler is under is identical at each time step. This is not true for classical reinforcement learning. So for example, if you look at Go, the state of a of the Go board is the state of the environment, and obviously the move you will make depends on that state. In chess, the position on the board is your state and the move depends on that. In the robot, depending on what the robot's position of the joints are, that's the state of the robot, and your move will depend on the current configuration of the robot. Video games, depending on where you are in your video game, your action is going to depend on that. So state of the environment, and that is what gives complexity to classical reinforcement learning, because you have environments in which the system has a state, and as we'll see, the number of possible states can be very large, and that's what causes many of the problems in reinforcement learning settings. So let's look at some examples. So let's familiarize ourselves with the basic terminology we'll be using repeatedly. So there are 5 terms that we'll be using repeatedly. One is agent, environment, state, actions, rewards. So I'm going to look at 4 settings. One setting is that there's a mouse in a maze trying to find a path towards cheese, which is the reward of the mouse. The second setting is there's a chess player playing a game and the chess player is trying to win the game, and that's the reward of the chess player. The third is the Multiarmed Bandits, which we just saw, where the bandit is playing slot machines and they get a reward at each timestamp. And the final is the robot, where the robot is trying to perform a locomotion, and depending on how much progress the robot makes, the robot gets some reward. Now note that in these settings, in some of them you get the reward at the very end. For example, in chess you get the reward at the very end. In some, for example, the Multi-Armed Bandits, you get continuous rewards. In each timestamp you get a continuous reward. So in the mouse example, the mouse is the agent, the chess player is the agent for the chess game. For the Multi-Armed Bandits, the gambler is the agent, and for the robot locomotion, the robot is the agent. Agent is essentially the entity your AI, your artificial intelligence is trying to train. It's trying to train your agent to make decisions. This is the entity that your system is designed to make it intelligent. Then you have an environment. Environment is essentially the rules of the game. The way in which the rules of the particular setting you are in, they react to your actions. So for example, the maze is the environment for a mouse trying to search for cheese. The chess rules are the environment for a chess game for a player, because the player can't just make any move, and depending on what move the player makes, the state of the system changes. Then the slot machines, the rules by which the slot machines give you payoffs, the probabilities with which the slot machines give you payoffs in the Multiarmed Bandit, that's the environment. And for a robot, assuming you are using a virtual simulator, it could be a virtual test bed for your robot. That's the environment. And the state, essentially, where is the agent at currently? Because the action of the agent is going to depend on their state. So the mouse, depending on where they are in the maze, their actions will depend on where they are. Whether it should make a left turn or whether it should make a right turn, it depends on where the mouse is in the maze. Similarly, the chess player, what moves the chess player should make depends on the position of the board. So the state of the board is the state. Now the Multiarmed Bandit is interesting because it's stateless. So the state is always unchanged. And in the case of the robot locomotion, the robot joints that are the state. Then the actions, in the case of the mouse, is the turn in the maze, it's a move in chess is the action, pulling a slot machine lever is the action for the Multiarmed Bandits, and the robot making a step is the action in the case of robot locomotion. And the rewards are cheese for mouse, winning a chess game, the payoff for the slot machine, and the virtual robot reward. So you can look at the basic framework of reinforcement learning. So let's look at it from the mouse going through the maze analogy. What's the sequence of actions, how these states, rewards, and actions that we discussed in the previous, how they relate to one another. So the agent, which is the mouse, it takes an action. So let's say it's a left turn in the maze from a particular state. That's the position of the mouse in the maze, which is ST. And if the mouse made a correct decision, so if it made a left turn and then it found some cheese, the environment will give the mouse reward RT. That's whether it gave it a cheese or no cheese. And then the state of the agent is changed, because when the mouse made a left turn, it's in a different position in the maze. So obviously the next action that it needs to make depends on that state. It is stateful. And depending on where the mouse got a reward or not, the neurons in the mouse's brains are going to update. This information on whether the mouse got a cheese or not, and that's at the core of reinforcement learning. So the next action that the mouse takes will be with this additional knowledge. And as we'll see, the AI framework, this exact sequence is what is done in our AI framework, especially when we use deep learning. This is exactly what we do. So you can view this as a Markov decision process where your state, action, reward. So you have S0, which is a state at timestamp 0, then A0, action at timestamp 0, and then the environment gives the reward R0, and then S1, A1, R1. So this is a Markov decision process. Now note that these Markov decision processes can be finite or they can be infinite. If they are finite, they are referred to as episodic. So for example, if you play tic-tac-toe, your Markov decision process, there are 9 positions on the board, so any particular game can be no more than 9 moves. So your Markov decision process has length at most 9. But there are certain settings which, like for example, robot locomotion, the robot may always be on, so you can view it as an infinite decision process. And this has some consequences to the algorithms, as we'll discuss later. Now let's look at some other examples of Markov decision process. I already introduced some terminology. So for example, if you have a game of tic-tac-toe, chess or go, the state is the position of the board, the actions correspond to the move made by the agent, and the reward is +1, 0 or -1 depending on which is received at the end of the game. Now this part I want to emphasize that in many reinforcement learning settings, in some you receive rewards continuously at each timestamp, and in some you receive at the end, and in some you receive them in a delayed way. This delayed aspect of the reward is a very critical part of the learning that happens in reinforcement learning. In fact, it's at the heart of conventional reinforcement learning. It's called the credit assignment problem. See, because what happens is that when you play chess or tic-tac-toe, you might set a trap for your opponent, but you don't get that reward immediately for setting that trap. You get the reward at the end of the game. So somehow your reinforcement learning needs to learn the fact that there's a value to setting that trap. And this is at the heart of conventional reinforcement learning. And we will look at an example using tic-tac-toe in the upcoming slides. Similarly, in a robot locomotion, the state corresponds to the current configuration of robot joints and its positions. The actions correspond to torques applied to the robot joint. The reward at each time is a function of whether the robot stays upright and the amount of forward movement. In a self-driving car, the states correspond to sensor inputs from the car sensors, and the actions correspond to the steering, axle, and braking choices. The reward is a function of the car progress and safety. So, let's look at the role of traditional reinforcement learning. Now, right now, we are not going to worry about deep learning. We're just going to look at very conventional reinforcement learning. It's called table-centric reinforcement learning, where deep learning is not needed. So let's look at a game of tic-tac-toe for which traditional reinforcement learning actually works. As we'll see, there are many settings like chess where traditional reinforcement learning doesn't work. You need techniques like deep learning. So the goal of traditional reinforcement learning is to learn how to make moves. So assume that your agent is a tic-tac-toe player. So it decides where to make moves. Now let's say that your tic-tac-toe player is playing X and you are playing the O's. And the way your reinforcement learning system is going to work is that it's going to learn through trial and error the long-term value of each state. I emphasize the word long-term because this is the credit assignment which is at the heart of reinforcement learning. So I have shown you two positions in tic-tac-toe. Now note that if you look at the position on the left, playing X here assures victory with optimal play. But that victory will not be realized until a few moves down the road. So that's the goal of traditional reinforcement learning, to perform this credit assignment, to learn that, oh, this was a trap. And this move should somehow be credited more in my table of action to reward. So just as in your Multiarmed Bandit, the gambler learned playing which slot machine gave it the most reward because in the presence of stochasticity, here in the presence of delay, the person needs to learn which action will give the best long-term reward. So that's at the heart of it, that the rewards are not realized immediately because of a variety of factors. It could be stochasticity, as we saw in Multiarmed Bandits, or it could be because of delay in a board game. But your reinforcement learning algorithm should be able to see through these delays or stochasticity. So we are going to look at reinforcement learning for tic-tac-toe. In fact, we'll give a simple algorithm, just as we gave a simple algorithm for the multi-armed, we gave epsilon greedy for multi-armed bandits. We are going to work out an epsilon greedy algorithm for tic-tac-toe. Now, the main difference from multi-armed bandits is that we need to learn the long-term rewards for each action in each state. So here the point is that an eventual victory earns a reward from a +1, 0, -1 with delay. So what we are going to do is that we are going to use a notion of discounted rewards. And as you'll see, discounted rewards are very common in reinforcement learning. So we have a parameter gamma which is less than 1. Let's say gamma is 0.95, something like that. And a move that occurs R moves earlier than game termination will earn a discounted reward of gamma to the power R minus 1. So if the system wins after making that move, after R moves, they will get a reward of gamma to the power R minus 1, or it will get 0 or minus gamma to the power R minus 1. And the future rewards would be, and the reason you have the discount is because you don't know how much that move contributed. So for example, if a move wins immediately, you know for sure that move contributed to the win. Whereas for one of the earlier moves, you're not certain how much it contributed. And if you replayed that same game with that same move, the future reward would be less certain. So that's why you tend to discount the earlier moves. And that's generally true in all kinds of settings. Even in finance, future rewards are always less than immediate rewards. And now, you assume that a fixed pool of humans is available as opponents to train the system. Now, that's not necessary. In fact, most game-playing reinforcement learning systems, they learn via self-play. And in fact, both work. In fact, self-play is better because you can generate unlimited amounts of data by playing the system against itself. So, Let's look at how we'll generalize epsilon greedy to tic-tac-toe. So remember that in Multiarmed Bandits, we just needed to maintain the average payoff of each slot machine. So for each action, you had a value. But here, you have a notion of states. So now, instead of maintaining a value for each action, you will maintain a table of values for state action pairs. So that's the only difference, because now you have the notion of a state. Instead of maintaining average value for each action, you're maintaining the average value. So for each position in tic-tac-toe that you have seen, you're maintaining, when I was in this state and I played this move, what was the average reward I got? And the average reward, depending on what happens at the end of the game, you're going to give this move some credit based on the discount. So the way it will work is that you're going to use the epsilon greedy algorithm. So you have the current table containing your values for each action in each state. So you're going to start off with a table with small random values. And you're going to use, for each state that you encounter, you're going to look up your table, what's the value of that state, and then you're going to play the optimal move based on by comparing among the actions. But you'll also, to encourage exploration, you'll also play a random move with some probability epsilon. So it's an epsilon greedy algorithm. And then you're going to play this game to termination. Now, you can do this using self-play. So the reinforcement learning system will always make the best move from the perspective of each player. And after the game, you will increment at most 9 entries in the unnormalized table with values from gamma to the power r minus 1, 0, minus, after for r moves to determine and win-loss. So, for example, if you're doing self-play and let's say the crosses win over the O's. So for all the crosses, for all the moves made by the crosses, you're going to give gamma to the power r minus 1 credit. And for all the actions that correspond to the moves for O's, you're going to give minus gamma to the power r minus 1 for those possible actions. And this is how your table will always maintain the average value of each action in each state. So you're going to have an exhaustive table for every possible board position in tic-tac-toe and every possible action. Now note that tic-tac-toe is a very toy game. You can show that there are fewer than 20,000 states on the board, so it's not very difficult to create a table for every possible configuration of tic-tac-toe and every possible action. And if you look at, so for example, when you perform this game and you create this table, so I've given examples of 4 entries from this table. This is a table of state action pairs. And you can see that these are just illustrative examples. They are not outputs from an actual game or an actual reinforcement learning system. But you can see that the ones that correspond to traps, the 2 moves that correspond to traps will typically have higher values. And the ones that correspond to moves that aren't so good, they won't have such high values. The reason for this is that your reinforcement learning system, through trial and error, when it went through the epsilon greedy algorithm, very often it will get to the situation where it played the trap by chance and then it earned a reward, because often it led to victory. So what happens is that the reinforcement learning system, this epsilon greedy algorithm, it learns the strategic value of the moves. So even though there's delay in the reward, we were able to learn what the strategic value of each move is. Now note that here we were putting state action value triplets in the table. In reality, you can work with state value pairs and you can just look at one move to see what state you will be in and make the optimal move. So you don't necessarily need to keep the triplets, you can just keep state value pairs. And now, where does deep learning fit in? Now, one point is that if you look at this specific example, this tic-tac-toe is a glorified learning by rote algorithm. Why do I call it learning by rote algorithm? Your algorithm has to see every state in the board, every valid state in the board. It will see every valid state in the board in order to become a good player. So the only reason why it learned these high values for these traps is because it saw them before, during its learning. And because it saw them before, it saw them multiple times, it saw victories multiple times from these states, it was able to assign high values to them. What this means is that this kind of approach can only work for toy settings with a few states. So tic-tac-toe is one example because there are at most 20,000 states on the board, and the number of actions is also very limited. So it's very easy to tabulate the values for states and action pairs. Now, if you look at, for example, chess, the number of board positions in chess is huge. In fact, humanity has explored only a very minuscule fraction of all the possible positions in chess. Now, the goal of deep learning is to serve the role as function approximation. You need to be able to generalize to unseen states. So if I see a new state on the board, a state I haven't seen before, I need to be able to say what its value is. I don't want to have to go to a table for that state and look at the value of each action. I want to be able to somehow estimate as a function of the state what the value of the state is. So that's a function approximator. So rather than a table of state action pairs, we can have a neural network that maps states to values. And instead of learning the table of state action pairs, you are learning the parameters of the neural network which are substituting for the table. That is how, because chess has just too many states for you to learn all the values of every action in every state explicitly. So let's look at a strawman epsilon greedy algorithm with deep learning for chess. Now this is a very primitive algorithm, it won't work very well, but it gives you the basic principle. This is generalizing the tic-tac-toe algorithm to chess. How would one go about it? So we have a convolutional neural network which takes the board position as the input and produces the position value as output. Now you can also have, you can also produce as output the values of each possible action. And you can use the epsilon greedy algorithm on the values of on the output values to simulate a full game. This was exactly what you were doing in tic-tac-toe, except that in tic-tac-toe you were going back to a table, accessing it. Here you are using a neural network as a function approximator. And after a game of X moves, so let's say your game lasted for 50 moves. And after 50 moves, and one side won or lost, you create 50 training points with the, and each of the training point will have a board position, one of those 50 board positions as the input feature map. And the target will be from gamma to the power r minus 0 minus gamma, depending on what was the move number. So if it was a final move which gets a checkmate, the value will be 1, 0, minus 1, because that's a sure checkmate. But among the earlier moves, you're not sure how much that contributed to the victory, so you're going to discount a little bit. Let's say gamma is equal to 0.99, and the one among the earlier moves, you're going to credit a little bit less. And you can update a neural network with these X training points. So here you are updating the parameter of the neural network. In tic-tac-toe, you updated the table, the average values are maintained in the table. Here you are updating the parameters. And you will repeat the steps. And this is going to give you a trained neural network. So at inference time, what you're going to do is that you're going to use this trained neural network to predict the values of moves, and then just pick the best move. You can even use some look ahead. You can even combine it with a minimax tree in order to give you a better move. In fact, the algorithm that I discussed is too naive to work well, but a very sophisticated algorithm that learns tic-tac-toe that learns chess, go, and shogi has been designed by DeepMind. And of course, this technique is far more advanced than the naive approach that I discussed in the previous slide. This uses advanced deep learning methods and Monte Carlo research. In fact, it's described in the book. The go algorithm is described in the book, and even some of the portions of the chess algorithm are described in the book. And what you find is that a neural network learns the values of states very well through trial and error. In fact, when you compare it to conventional chess software, it plays far more positionally, and sometimes even it makes sacrifices, much like a human does, because its trial and error tells it that certain types of positions, certain patterns in particular positions are advantageous for making certain types of moves. And if you compare it with in fact, it won over the best handcrafted evaluations, conventional chess software using handcrafted evaluation, which is Stockfish, quite handily. So, for example, while playing as white, it won 50% of its games. And just to give you an idea, here I have shown two examples of these games of chess between AlphaZero and Stockfish. And in both cases, alpha 0 is white and stockfish, which is the conventional chess software, is black. So if you look at the position on the left, you can see that white has fewer pawns than black, and in fact black has a passed pawn. So white has actually made some sacrifices, but what white has done is that the light square bishop of black, it's trapped behind its own pawns. So this is a very positional move. This is the kind of thing that a human player would do. And because of this, after a very large number of moves, and typically that number of moves was larger than the horizon of the conventional chess playing software, this alpha 0, it won the game. Similarly, if you look at the position on the right, the white is down by a lot of material. In fact, it's down by 2 pawns and in exchange of a bishop for a rook. And you can see that here black is completely paralyzed, its queen is completely trapped, none of its rooks can move, and victory is actually imminent for white in a few moves. So these kinds of positional factors, they cannot be easily learned by conventional chess software. The reason that the deep learning system was able to learn this is because through trial and error, it saw many similar positions, not exactly the same position. These are unseen states. Most likely the deep learner did not see these specific states, but it learned over time that board positions containing similar patterns, similar positional patterns where I constrict the opponent in this way, they are good for me. And that's how it is able to win. Now, there are other challenges associated with deep learning. One is that chess and tic-tac-toe, they are episodic. So there's a maximum length to the game. So for example, it's 9 for tic-tac-toe and 6000 for chess. And if you look at the epsilon greedy algorithm, it updates episode by episode. So after the whole chess game is over, it updates the moves. Now, what about infinite Markov decision process like robots or long episodes? In these cases, the rewards are received continuously, and you want to do online update. You want to update after each move. It's not optimal to update episode by episode. So there are techniques called value function learning and Q learning, which can update after each step, after each move with the use of Bellman's equations. And this will be the topic of our next lecture.